Welcome to This Explainer. Today, we're diving straight into the absolute foundation of our digital world. Have you ever stopped to wonder how a really simple combination of just two numbers, 0 and 1, can somehow give us everything, from breathtaking video games to massive global communication networks and even artificial intelligence? Well, we are unpacking the architecture of computing today. We're going to look at the actual hardware that makes this all possible and figure out exactly why data absolutely must be represented this way. To kick things off, let's contrast our continuous, everyday analog reality with the digital realm of our devices. In the real analog world, things exist on a continuous spectrum. Think about turning down a light with a dimmer switch. If we could slow time right down, you'd see this really gradual, sweeping decrease in light, a continuous, smooth line just fading into darkness. But our computing devices, they don't operate like that at all. In the digital world, this light exists in only one of two discrete states. It's either completely on or completely off. It switches instantly between them, with literally zero in between.
All right, so that brings us to section 1, our analog world versus digital binary.
To really understand binary, we kind of have to look at how we naturally count as humans. Ancient civilizations developed the base 10 denary system, the numbers 0 through 9, and that's likely just because we have 10 fingers to count on. It feels perfectly natural to us. But your computer doesn't have hands. It relies entirely on a base 2 number system, which we call binary. A single binary digit, or bit, is the basic building block of computing, and it can only ever be a 0 or a 1. Any form of data, no matter how wild or complex, absolutely has to be converted into this binary format for a computer to process it.
Let's move right along to section 2, why computers choose binary.
So you might be wondering, why use only zeros and 1 instead of the 10-digit system we're all used to? It's a great question, and the answer has absolutely nothing to do with software preference. It's entirely about hardware efficiency, cost, and reliability. You might think a 10-digit system would make computers smarter, but physically trying to build that? Total nightmare. Under the hood, your computer is basically made up of millions and millions of tiny switches. It is vastly cheaper and way less prone to error to build components that only ever have to detect two distinct physical states. Take your computer's RAM, for example. Data there is represented by these microscopic capacitors that either hold an electrical charge, that's a 1, or don't hold a charge, that's a 0. On a hard disk, it's magnetic north or south. On a CD, a laser either reflects off the surface or it doesn't. Just imagine if hardware had to accurately detect 10 different, highly specific levels of electrical charge to match our denary system. It would be incredibly difficult to manufacture and so prone to error, like misreading a 6 as a 7 all the time. Binary keeps the hardware beautifully simple and perfectly reliable. But here's where the real magic happens: the combination. Grouping these simple bits together allows us to represent complex text, images, sounds, the whole shebang. This brilliant concept was formalized by a mathematician named Claude Shannon. He's actually credited with inventing digital circuit design way back in 1937. He literally laid the exact groundwork that is powering the device you're using right now. Which leads us to section 3, logic gates and switches. Okay, just as we need food, computers need electricity to run. But electricity entering a computer generally comes in at one set voltage. So to get our two binary states, computers use tiny little components called logic gates. Think of them as microscopic switches that control the flow of electricity. They take incoming electrical currents and output either a high voltage, which the computer reads as a 1, or a low voltage, which it reads as a 0. These gates apply basic Boolean operations, basically logical rules deciding if a statement is true or false to make decisions. So the absolutely crucial takeaway here is the sequential journey of data within the system. Before you see a single result on your screen, 3 things happen. First, the data input is converted into that binary format. Second, it's processed through the physical logic gates we just talked about to carry out the calculations. And third, the results of those calculations need a place to sit temporarily so the computer doesn't lose track of them. And that temporary storage is section 4, registers. So what is a register? Registers are incredibly fast access holding places located directly inside the CPU. They act kind of like a super efficient workspace on a desk. And as you can see, there are different types of registers for different jobs. The accumulator, or ACC, holds numbers temporarily while calculations are happening. The memory address register tracks exactly where in the system's memory data needs to go. Actually, to pair with that, the memory data register holds the actual data itself. The program counter tracks what instruction is coming up next, and the current instruction register holds the command that's currently being decoded. Working together, these registers juggle millions of ones and zeros perfectly in sync.
All right, let's zoom out a bit for section 5, translating everything into binary.
Let's start with text. When you type on your keyboard, the computer uses a character set to translate your keystrokes into binary code. An older, really common set is ASCII, which uses an 8-bit binary number for each character. That gives us up to 256 characters, which is fine for standard English. But the world is huge, right? To handle global alphabets like Mandarin or Arabic, and yeah, modern emojis, we upgraded to Unicode. Unicode uses 16-bit binary numbers, dramatically expanding our capacity to roughly 65,000 different characters.
And this is a great visual for how binary maps to images. Think about the digital images you're looking at every day. In its simplest form, a computer just sees a digital image as a giant grid of pixels. For a black and white image, the computer simply assigns a 0 for a white pixel and a 1 for a black pixel. By combining thousands of these pixels, an image emerges. The more pixels you have, the higher the resolution. And if you add more bits per pixel, which we call color depth, you can tell the computer to display millions of different colors. It's like a giant, super fast mosaic. So we've seen how binary is basically the ultimate compromise between human necessity and hardware reality. By reducing the messy, continuous analog world into distinct on and off states, we've built a remarkably reliable digital ecosystem. But as we continue to push the boundaries of technology, looking at innovations that defy traditional electronics, it leaves us with a really exciting, provocative question. If ones and zeros built everything we know today, what does the future of computing look like when we finally invent hardware that breaks past the limits of binary? Thank you so much for joining me in this explainer. Keep asking questions and keep learning.